Object-oriented approach. Object-oriented approach includes objects, classes, inheritance, and communication between objects. The key ideas are objects, encapsulation, class and inheritance, and messages. The object encapsulation data, operations, other objects, constants, and other related information. Class attributes can be reused. Encapsulation means that all of this information is packaged under one name. It can be reused as one program component. Examples for inheritance. Message format in communication. Message, destination, operation, parameters. Objects communicate by sending messages to each other. Conclusion. In this chapter, we have covered the following in detail. Software program and its objective, software development techniques, top-down versus bottoms-up approach, modular programming, structures programming, introduction about object-oriented approach. Learning objectives. In this chapter, the user will learn the following in detail. Software program and its objective, software development techniques, top-down versus bottoms-up approach, modular programming, structures programming, introduction about object-oriented approach. Modular and structures programming. Modular programming. Modular programming is the process of subdividing a computer program into separate subprograms. A module is a separate software component. It can often be used in a variety of applications and functions with the other components of the system. Modules can be reused by other applications. Structured programming. Structured programming is an important component-level design technique. Fundamental constructs of structures are sequence, condition, and repetition. Sequence implements processing steps that are essential in the specification of any algorithm. Condition provides the facility for selected processing based on some logical occurrence. Repetition allows for looping. Software development techniques. Software development strategies are called as a process model or a software engineering paradigm. Process models for software development. Linear sequential model, prototyping model, rapid application development model, evolutionary software process models, component-based development, the formal methods model, fourth generation technique. Linear sequential model, the classic lifecycle model, or the waterfall model. It suggests a systematic sequential approach to software development. It begins at the system level and progresses through analysis, design, coding, testing, and support. Software requirement analysis. The requirements gathering process is intensified and focused on software to understand the nature of the programs to be built. Design. Software design is actually a multi-step process that focuses on 4 distinct attributes of a program: data structure, software architecture, interface representations, and procedural, algorithmic detail. Code generation. The design must be translated into a machine-readable form. The code generation step performs this task. Testing. It focuses on the logical internals of the software. It uncovers errors and ensures that defined input will produce actual results. Support maintenance. Software must be adapted to its external environment or customer requires enhancements. It reapplies each of the preceding phases to an existing program. Advantages of Waterfall model. Easy to understand, easy to use. Milestones are well understood. Sets requirement stability. Works well when quality is more important than cost or schedule. Drawbacks of Waterfall model. Real projects rarely follow the sequential flow. Changes can cause confusion as the project team proceeds. It is often difficult for the customer to state all requirements explicitly. A major blunder, if undetected until the working program is reviewed, can be disastrous. Linear nature of this process leads to blocking states. Some members must wait for other members of the team to complete dependent tasks. The prototyping model. When do we need the prototype model? When the customer defines a set of general objectives for software but does not identify detailed input, processing, or output requirements. When the developer may be unsure of the efficiency of an algorithm, adaptability of an operating system, etc. The prototyping paradigm begins with requirements gathering. Developer and customer meet and define the overall objectives for the software. When the requirements are known, the quick design is created. The quick design focuses on a representation of those aspects of the software that will be visible to the user. The quick design leads to construction of a prototype. Assessment or user evaluation. The proposed system is presented to the user for consideration as part of the development process. Prototype refinement. Once the user evaluates the prototype, it is refined according to the requirements. When the user is satisfied with the developed prototype, a final system is developed based on the final prototype. Engineer product. The final system is thoroughly evaluated and tested, followed by routine maintenance on a continuing basis to prevent large-scale failures and to minimize downtime. Advantages of prototype model. Prototype is evaluated by the user and used to refine requirements of the software. If a working prototype is built, the developer attempts to use existing program fragments that enable working programs to be generated quickly. Actual software is engineered with an eye toward quality and maintainability. Drawbacks of prototype model. Compromises on the quality of the product. The developer often makes implementation compromises. An inappropriate operating system or programming language may be used. An inefficient algorithm may be implemented simply to demonstrate capability. This model leads to false expectations. Often the user believes that the development of the system is finished when it is not. Rapid Application Development Model. Rapid Application Development, RAD, is an incremental model. It is an extremely short development cycle. The RAD model is a high-speed adaptation of the linear sequential model. Rapid development is achieved by using component-based construction. If requirements are well understood and project scope is constrained, the RAD process enables a development team to create a fully functional system within a very short time period, that is, 60 to 90 days, used primarily for information system applications. Figure shows the rapid application development process. The RAD approach encompasses the following phases. Business modeling. The information flow among business functions is modeled in a way that answers the following questions. What information drives the business process? What information is generated? Who generates it? Where does the information go? Who processes it? Data modeling. The information flow is refined into a set of data objects. Attributes of each object are identified and the relationships between these objects are defined. Process modeling. To achieve the information flow necessary to implement a business function, processing descriptions are created for adding, modifying, deleting, or retrieving a data object. Application generation. RAD assumes the use of fourth-generation techniques. The RAD process works to reuse existing program components. Testing and turnover. Many reused components are already tested. However, the new components must be tested and all interfaces fully exercised. Advantages of RAD. Reduced development time. Increases reusability of components. Integration from very beginning solves a lot of integration issues. Many of the program components have already been tested. This reduces overall testing time. Automated tools are used to facilitate construction of the software. Drawbacks of RAD. For large but scalable projects, RAD requires sufficient human resources to create the right number of R&D teams. Requires highly skilled developers, designers, to get a system complete in a much abbreviated time frame. If commitment is lacking, R&D projects will fail. Only systems that can be modularized can be built using R&D. R&D is not appropriate when technical risks are high, when a new application makes heavy use of new technology, or when the new software requires a high degree of interoperability with existing computer programs. Evolutionary software process models. Evolutionary models are iterative to develop increasingly more complete versions of the software. Incremental model, spiral model, win-win spiral model, concurrent development model. Incremental model. It combines elements of the linear sequential model applied repetitively with the iterative philosophy of prototyping. It applies linear sequences. Each linear sequence produces a deliverable increment of the software. For example, word processing software developed using the incremental paradigm might deliver basic file management, editing, and document production functions in the first increment, more sophisticated editing and document production capabilities in the second increment, spelling and grammar checking in the third increment, and advanced page layout capability in the fourth increment. When an incremental model is used, the first increment is often a core product. The core product is used by the customer. As a result of use, a plan is developed for the next increment. The plan addresses the modification of the core product to meet the needs of the customer and delivery of additional features and functionality. This process is repeated following the delivery of each increment until the complete product is produced. Figure shows the incremental process model. Advantages of incremental model. Parallel development can be planned. Progress can be measured. Less costly to change the scope or requirements. Testing and debugging during smaller iteration is easy. Drawbacks of incremental model. More resources may be required. Not suitable for smaller projects. Highly skilled resources are required for risk analysis. The spiral model. It is an evolutionary software process model that couples the iterative nature of prototyping with the controlled and systematic aspects of the linear sequential model or the waterfall model. It provides the potential for rapid development of incremental versions of the software. During early iterations, the incremental release might be a paper model or prototype. During later iterations, increasingly more complete versions of the engineered system are produced. A spiral model is divided into a number of framework activities, also called task regions. The following figure depicts a spiral model that contains 6 task regions. Six task regions of spiral model. Customer communication. Tasks required to establish effective communication between developer and customer. Planning. Tasks required to define resources, timelines, and other project-related information. Risk analysis. Tasks required to assess both technical and management risks. Engineering. Tasks required to build one or more representations of the application. Construction and release. Tasks required to construct, test, install, and provide user support, that is, documentation and training. Customer evaluation. Tasks required to obtain customer feedback based on evaluation of the software. Task set. Each of the regions is populated by a set of work tasks. While the evolutionary process begins, the software engineering team moves around the spiral in a clockwise direction, beginning at the center. The first circuit might result in the development of a product specification. Subsequent passes around the spiral might be used to develop a prototype and then progressively more sophisticated versions of the software. Each pass through the planning region results in adjustments to the project plan. Cost and schedule are based on feedback derived from customer evaluation. The project manager adjusts the planned number of iterations required to complete the software. Advantages of Spiral Model. The spiral model is a realistic approach to the development of large-scale systems and software. The developer and customer better understand and react to risks at each evolutionary level. The spiral model uses prototyping as a risk reduction mechanism. Drawbacks of spiral model. It may be difficult to convince customers, particularly in contract situations, that the evolutionary approach is controllable. It demands considerable risk assessment expertise and depends on this expertise for success. If a major risk is not uncovered and managed, problems will undoubtedly occur. The win-win spiral model. When is this model needed to develop a software? When the customer and the developer enter into a process of negotiation, the best negotiations strive for a win-win result. That is, the customer wins by getting the product that satisfies the customer's needs, and the developer wins by working to realistic and achievable budgets and deadlines. The win-win spiral model is illustrated in Figure. It defines a set of negotiation activities. The following activities are defined: identification of the system or subsystem's key stakeholders, determination of the stakeholders' win conditions, negotiation of the stakeholders' win conditions to reconcile them into a set of win-win conditions for all concerned, including the software project team. This model introduces 3 process milestones called anchor points that help to establish the completion of one cycle around the spiral and provide decision milestones before the software project proceeds. Anchor points represent 3 different views of progress as the project traverses the spiral. The first anchor point, Life Cycle Objectives (LCO), defines a set of objectives for each major software engineering activity. For example, as part of LCO, a set of objectives establishes the definition of top-level product requirements. The second anchor point, Life Cycle Architecture (LCA), establishes objectives that must be met as the system and software architecture is defined. For example, as part of LCA, the software project team must demonstrate that it has evaluated the applicability of off-the-shelf and reusable software components and considered their impact on architectural decisions. Third anchor point is Initial Operational Capability (IOC), and it represents a set of objectives associated with the preparation of the software for installation or distribution, site preparation prior to installation, and assistance required by all parties that will use or support the software. The Concurrent Development Model, Concurrent Engineering. The concurrent process model can be represented schematically as a series of major technical activities, tasks, and their associated states. For example, the engineering activity defined for the spiral model is accomplished by invoking the following tasks: prototyping and/or analysis modeling, requirement specification, and design. The following figure provides a schematic representation of one activity with the concurrent process model. All activities exist concurrently but reside in different states. For example, early in a project, the customer communication activity has completed its first iteration and exists in the awaiting changes state. The analysis activity, which existed in the none state while initial customer communication was completed, now makes a transition into the under development state. If customer indicates that changes in requirements must be made, the analysis activity moves from the under development state into the awaiting changes state. The concurrent process model defines a series of events that will trigger transitions from state to state for each of the software engineering activities. For example, during early stages of design, an inconsistency in the analysis model is uncovered. This generates the event analysis model correction, which will trigger the analysis activity from the done state into the awaiting changes state. When applied to client-server, the concurrent process model defines activities in two dimensions: system dimension, component dimension. System-level issues are addressed using three activities: design, assembly, and use. The component dimension is addressed with two activities: design and realization. Concurrency is achieved in two ways. System and component activities occur simultaneously and can be modeled using the state-oriented approach described previously. Client-server application is implemented with many components, each of which can be designed and realized concurrently. Advantages of concurrent model. It is used for the development of client-server applications. The concurrent process model is applicable to all types of software development. It provides an accurate picture of the current state of a project. It defines a network of activities. Each activity on the network exists simultaneously with the other activities. Events generated within a given activity or at some other place in the activity network trigger translations among the states of an activity. Component-based development. Object-oriented technologies provide the technical framework for a component-based process model. Object-oriented paradigm emphasizes the creation of classes that encapsulate both data and algorithms used to manipulate the data. Object-oriented classes are reusable across different applications and computer-based system architectures. Component-based development model composes applications from pre-packaged software components called classes. This is accomplished by examining the data to be manipulated by the application and the algorithms that will be applied to accomplish the manipulation. Corresponding data and algorithms are packaged into a class. The concurrent model is illustrated in Figure 1. Classes created in existing projects are stored in a class library or repository. Once candidate classes are identified, the class library is searched to determine if these classes already exist. If they do, they are extracted from the library and reused. If a candidate class does not reside in the library, it is engineered using object-oriented methods. The first iteration of the application to be built is then composed using classes extracted from the library and any new classes built to meet the unique needs of the application. Process flow then returns to the spiral and will ultimately re-enter the component assembly iteration during subsequent passes through the engineering activity. The formal methods model. This model has formal mathematical specification of computer software, used to specify, develop, and verify a computer-based system by applying a rigorous mathematical notation. A variation on this approach called clean room software engineering. When formal methods are used during development, they provide a mechanism for eliminating many of the problems that are difficult to overcome using other software engineering paradigms. Advantages of formal methods model. Ambiguity, incompleteness, and inconsistency can be identified and corrected more easily. During design, they serve as a basis for program verification. Formal methods model offers the promise of defect-free software. Drawbacks of formal methods model. The development is time-consuming and expensive. Extensive training is required. It is difficult to use the models as a communication mechanism for technically unsophisticated customers. Fourth generation techniques, 4GT, encompasses a broad array of software tools. The tool automatically generates source code or a model composed of a network of graphical icons. Implementation using a 4GT leads to automatic generation of code to create desired results. The fourth generation technology is illustrated in Figure. Advantages of 4GT. 4GT is a viable approach for many different application areas. 4GT offers a credible solution to many software problems. Use of 4GT reduces the time to produce software for small and intermediate applications. Reduces the amount of design and analysis for small applications. Drawbacks of 4GT. The use of 4GT without design for larger projects leads to less quality and poor maintainability. Software program and its objective. Software program. Software program is a sequence of instructions that, when executed, provide desired function and performance. Software that controls an automated machine. Types of software. System software. Application software. System software. To run a computer's hardware and application programs. Application software. To interact with system software. Then, system software directs computer hardware to perform the necessary tasks. Application software has two types. Proprietary software. Off-the-shelf software. Proprietary software. Program for a specific application, usually developed and owned by a single company. Off-the-shelf software. Existing software program that is purchased. Software engineering. Software engineering is a systematic approach to the design, development, operation and maintenance of a software system. Objectives of software engineering. Maintainability, ease with which changes in a functional unit can be performed. Reusability, extent to which module can be used in multiple applications. Portability, ease with which software can be transferred from one computer system or environment to another. Reliability, attribute of software quality, the extent to which a program can be expected to perform its intended function over an arbitrary time period. Adaptability, ease with which software allows differing system constraints and user needs to be satisfied by making changes to the software. Top-down versus bottom-up approach. Top-down approach. First, start with a clear statement of the problem or concept. Next, break it down into several parts. If any of those parts can be further broken down, then the process continues. The final design showing the overall structure of separate units that form a single complex entity. Top-down design leads to modular development, that is, the process of developing software modules individually, then combining the modules to form a solution to an overall problem. Bottom-up approach. The bottom-up design model starts with most specific and basic components. It proceeds with composing higher level of components by using basic or lower level components. It keeps creating higher level components until the desired system is not evolved as one single component. With each higher level, the amount of abstraction is increased. Bottom-up strategy is more suitable when a system needs to be created from some existing system where the basic primitives can be used in the newer system.